All right, problem 2, homework 10. Problem 2 is related to problem 1 of homework 10, where we deal with this Poisson process. So I wrote the equation down here again. And I remind everyone from problem 1 that expected value of x is lambda t, where x is this interval over here of n from 0 to t. So, part A. So they give us some information before part A. They say expected value of x of 9 is equal to 6. And then at A they ask us to find a specific case. So, we know that t is equal to 9 in this case, and that lambda t is equal to 6. So lambda t equals 6. T equals 9. So let's plug that in. Lambda times 9 equals 6. So lambda equals 6 over 9, or 2/3. So this is important. Now we're going to go to part A. Part A says find the mean and the variance of x of 8. So the mean is easy. We just do expected value of x of 8. And we use the formula. Expected value of x of 8. Right, so lambda times t, which is equal to, we know lambda is 2/3, t is 8. So we get 16 over 3. Now, the variance is equal to expected value of x squared, which we also proved in homework, in problem 1, minus expected value of x, everything squared. So this guy, if we recall from homework, from problem 2, was equal to lambda squared t squared plus lambda t. So we'll just recall that from problem 1. So expected value of x squared, I forgot to put the t. X squared at 8, well, that's just going to be lambda squared 8 squared minus expected value of x squared, which is 2/3 times 8 everything squared. Well, we forgot to plug in here lambda. Lambda is 2/3 squared, 8 squared. Well, we can write. Let's see. I forgot something. Expected value of x squared is this. So that's going to be lambda squared, which is 2/3 squared times 8 squared plus 2/3 times 8 minus 2/3, right, because it's squared, times 8 squared. These cancel, and we're just left with this, which is 16 over 3. So that's part A. Part B, right over here. Part B asks us to find the probability of x of 2 less than or equal to 3. So because it's discrete, we don't use an integral, we just use the summation. And we use the formula. So this is the summation from k goes from 0 to 3, because usually it's from minus infinity to infinity, but in this case we go from 0 onward. It's the Poisson process. So we have e to the so we have minus alpha is 2/3, but t is 2. So we multiply that. Then we have lambda t, which is 2/3 times 2 to the power k over k factorial. So this becomes e to the minus 4/3 times 4/3 k over k factorial as k goes from 0 to 3. And if you do this summation and you plug in the numbers, you will get 0.0 0.954. Okay, now part C. Part C gives us a conditional probability. So they ask to find the probability of x of 4 less than or equal to 5 given that x of 2 less than or equal to 3. Okay, so here we have to be careful. Remember that this is what x is defined as. So in this case, we're concerned about the interval x of 4, which is n from 0 to 4. Here we have x of 2, which is the interval from 0 to 2. Now these overlap, so there's a problem there. We can't, if we're going to do normal conditional probability, we cannot separate the intersection because they're not independent, because they overlap. So we have to be a little clever. Let's say we call x of 2 equal to z. And let me write it like this. Z equals x of 2. W equals x of 4 minus x of 2. So now z is from this interval and w is in this interval. So we've essentially made these are independent. Two independent random variables. So let's just write that. Z and w are independent. That's great. But we don't have this in our conditional probability. We just have x of 4. This is okay because we have x of 2, so it's cool. Here, we have to be, again, a little clever. So we have x of 4 is less than or equal to 5. Well, I can add or subtract anything from both sides and the inequality still holds. So let's say I subtract x of 2. So what do I get? I get x of 4 minus x of 2 is less than or equal to 5 minus x of 2. Well, x of 2 is just z, so we can write this as 5 minus z. So let's rewrite the this probability, right? I can, for this piece, I can just write this because I'm going to compensate with this, right? This x of 4 less than or equal to 5 is the same as x of 4 minus x of 2 minus, x of 4 minus x of 2 less than or equal to 5 minus x of 2. I just added something to both sides, so it's legal. I can do that. So x of 4 minus x of 2 is just w, which is less than 5 minus z, given that z is less than or equal to 3. So my brackets don't match. Okay. So let's say, so by the way, the conditional probability, you have the probability of this intersect this divided by the probability of just this. We found the probability of this in part B, which is here. So I'm just concerned about the numerator of this conditional probability. So let's write, I'm just going to write it like this. Probability of z equals n intersect w equals m, where n and m are just some, they're an event. Now, because these are independent, we can separate them. Right? And using the formula that was given in problem 1, this guy over here, namely, we can write that this is equal to e to the minus, remember z is evaluated at x of 2, so we have a lambda 2 lambda 2 to the power n over n factorial. This one, w, the range is still 2. So we still write e to the minus lambda 2, right? Because between 2 and 4 it's just 2, the range, the distance. So we have this lambda 2 m over m factorial. Now n goes, we'll make this that n goes from 0 to 3. Here m goes from 0 to 5 minus z, where z is what we defined earlier. So now we're going to put the summations. So this is going to equal to the summation e to the minus lambda 2 n over n factorial times summation e to the minus lambda 2 m here, where n goes from 0 to 3 and m goes from 0 to 5 minus z. Now remember that z is a random variable, and z was this event, right? So z, which is equal to x of 2, we know x of 2 is less than or equal to 3. So this probability, if we're going to do in this case, the summation, not the integral, it goes from 0 to 3. So z goes from 0 to 3. So really, we can write this as a nested summation with z equal to n. Because that's the case. Z, whenever n equals a number, z will equal that number in that summation. So we can write, now we write the entire thing. So probability of x of, this is just, I'm just writing from the beginning, right? Because we've showed that this is equal to probability of w less than 5 minus z. Oh, I'm sorry. This is equal to probability of w less than 5 minus z intersected with z less than 3. So in order to have the conditional probability, we have to divide by probability of x of 2 less than or equal to 3, which was 0.954, which we found in part B. So again, this z really becomes an n, because z is z is x of 2, right? And the summation for x of 2 that we're evaluating is from 0 to 3. And n is going from 0 to 3, so z must be n. So let's come back. We have probability of x of 4 less than or equal to 5, given that x of 2 is less than or equal to 3, is equal to. So now we have this summation. This is the summation of n from 0 to 3. And this is m from 0 to 5 minus n. So it's like a nested summation. So here we get, I'm just going to multiply these two. So we have e to the minus 4 lambda. We have 2 lambda to the n plus m divided by n factorial, m factorial. And all this is divided by this summation, right, which was expected value of x of 2 less than or equal to 3. So this, I'll use a different index. K goes from 0 to 3. E to the minus lambda 2k over k factorial, which we show that this is 0.954. So really, this guy becomes So I'm just going to write it again. Okay, e to the minus 4 lambda 2 lambda n plus m over n factorial times 1 over 0.954. Well, now what you can do is you can use MATLAB or Python or whatever you want and write this code, code it, and you will get, after you run the program, you will get that this summation divided by this number gives you 0.967. So that's the probability. This conditional probability is equal to this, and that completes the problem.